this. So let's go with silver. What did you get for the formula for silver? Ag solid. That's correct. Silver is a fixed charge ion. Therefore, if I meant silver ion's Ag plus, I would have said ion. Since I didn't say ion, you can automatically assume it's got to be silver metal. It's not ion. Whereas, the variable charge is going to have some Roman numeral. So if it's iron 2, that's obviously not iron metal. Iron 2 is obviously ion. Nitric acid, we already know what that is. Oh, then you go, I recognize that pattern. What pattern is that? Single replacement. So AB plus BX yields AX plus B. Oh, that's simple. That's silver nitrate, BX, plus hydrogen. It's the formula for hydrogen. H2. We'll balance it later. I got gas formation. Nitrate salts aren't going to precipitate. I got gas formation. That means I have driving force. That means this reaction is going to occur? Yes or no?
Yes.
No, this reaction is not going to occur because this is not metathesis. This is redox. And the driving force for redox is stronger to weaker. If you want to use activity is stronger reducer to weaker reducer, or more active element to less active element. But that's wrong. Unfortunately, silver is less active. Hydrogen is more active. And so we can't use gas formation, we can't use precipitation. Those things don't work for redox. They only work for metathesis. And acid base, they can work too, but in this case, we have to look at this. And therefore, the driving force is this way. If the driving force is backwards, then what we say is no reaction. But even though we did the redox driving force, can we say that there's no reaction for redox? No. No, we can't. That's because we know that single replacement has some exceptions. Did you memorize the exceptions, or are you somewhat familiar with the exceptions? What are the exceptions for single replacement reactions? What are the exceptions for single replacement reactions? The easy thing, and your book does this, the easy thing is not to talk about the exceptions. The simplest thing is don't give you a problem like this, because this would be one of the exceptions. Why is this one of the exceptions? Single replacement is going to fail for this. I would not do this single replacement. It's wrong. I wouldn't do a single replacement because I know that's one of the exceptions. I can just look at it and tell right off it's one of the exceptions because, for this chart you want to look at once in a while, but for the exceptions you want to read every day. If you read the exceptions every day, I didn't give you that many. You should be able to tell me what it is. Should be automatic. Although spring break, who studies over spring break? So maybe not so automatic, but maybe it'll take you a little bit more time. Or maybe you don't want to learn the exceptions. If you don't want to learn the exceptions, then use the chart method. If you use the chart method, you don't have to memorize the exceptions. Because the chart method naturally, why are there exceptions in the single replacement? Somebody tell me that, and why should the chart method work? Whereas the single replacement might fail. You have a question? What's that? Well, A is actually an element. Silver, if I wrote it as this, then it would be metathesis. If this were silver ion plus nitric acid, then it's metathesis because we're dealing with a mixture of ions and we've got to figure out which ion combination is best. could be metathesis, it could be redox, but it would be redox, but not single replacement, it would be redox chart method. Silver ions are pretty decent oxidizers, so I'd worry about redox reactions too. That breeding familiarity, gives you, if we go through this once in a while and we see some elements that appear here on potential reaction, then we know, oh, I've seen that before, I've seen that, oh yeah, that's a powerful oxidizer. So I got to be aware there could be a reaction, that kind of thing. That kind of thing you want to do quickly, like this. Automatically, I wouldn't have been wasting my time. I know this is going to fail, single replacement. Automatically, I see it's going to fail. How? And so you should be able to rattle these off, quickly. That's what those tests are like, time tests. Time test is not always just memorize. I don't have this memorized. I just, it's just familiarity. I know that there's something. That's because I know HNO3 is what type of acid. I know that this is going to fail because HNO3 is it's not because it's a strong acid, it's because it's a I talked about two types of acids.
Weaker acid?
Not a weaker acid. It doesn't have to do with strong and weak. It has to do with mineral acid versus they say, I guess they say I should repeat things at least 3 times. I only said this once.
Oxidizing acid?
Oxidizing acid, right. Mineral versus oxidizing acid. I know it's going to fail, but the single replacement method does not work for oxidizing acids. It does not work for oxidizing acids because single replacement method assigns roles. The roles are A. What is A? What is B? What is X? A is reducer, B is oxidizer, X is spectator. But then, I know this chart, and I've read this chart, and nitrate is a spectator, whereas H plus is the oxidizer. Does that make sense to you? Nitrate is the spectator, H plus is the oxidizer. Is that making sense to you? It doesn't make sense to me because nitrate is a much more powerful oxidizer than H plus. So if you have this mixture and both H plus and nitrate are trying to take electrons, which one's going to be more successful at taking electrons, nitrate or H plus? Nitrate. So how can you call X nitrate the spectator? Is that going to work? No, it's absolutely going to fail. And so I already knew this was going to fail because nitrate is much more powerful oxidizer than H plus. Therefore, we to make this click, it's where we have oxidizing acids, or where we have anions that are more powerful oxidizer than the H plus cation. All acids have H plus, but something like this, HCl. HCl oxidizes H plus. Is chloride a more powerful oxidizer than H plus? No. In fact, chloride's not even an oxidizer. Chloride's what we call a reducer. This is not an oxidizing acid. This is a mineral acid. And so things like sulfuric acid, oxidizing acid. Nitric acid, oxidizing acid. Iodic acid, oxidizing acid, et cetera, perchloric acid, chloric acid. All those are oxidizing acids. Even hypochlorous acid, all those are oxidizing acids. So you have a choice. And the choice is not offered to you by Petrucci, by Krakowicz. Krakowicz doesn't talk about this. He doesn't talk about this because he doesn't put problems like this on your homework or on the test or in the book. You aren't going to see this. That's the easiest. We just don't put anything like this on there. But it turns out that if this was just one exception, then that's fine. But there are multiple exceptions, which I talked about each of the common ones. I forgot how many I did. 1, 2, 3, at least 3 or 4 exceptions. So either you memorize those so that you aren't fooled or tricked by the single replacement pattern, or you just use the chart method. The advantage of single replacement is very quick. So if you do know the exceptions, you can go through them, these types of problems pretty rapidly. But if you don't know the exceptions, then you might get the wrong answer, which would be much more costly than taking a little bit more time. And so anyway, single replacement's wrong. So what do we have to do? We have to use the chart method. So this one's going to be a little similar to the last one. Let me just go through it, save some time here. So what we want to do is we want to figure out, is there any reaction? Well, there's not going to be any metathesis reaction. Not ion combinations, so we'll work on. And so we inventory silver, metal, H+, nitrate, and water. Silver metal, oxidizer or reducer? Silver is only a reducer. Silver is not a very good reducer. Silver ion is a better oxidizer. But we have no silver ions, so we're stuck with silver metal. H+ is an oxidizer alone. H+ with nitrate, in other words, nitrate is an oxidizer. But nitrate's a great oxidizer, but there has to be some H+ present, which we have. We're dealing with nitric acid this time. We aren't going to worry about the ratio. We just have H+ and nitrate, the combination. And then water is an oxidizer reducer. And so which one's the strongest oxidizer? Water, H+, or nitrate? Nitrate and H+. So that's our oxidizer, H+ and nitrate. What's the strongest reducer? It's going to be silver. Water, that's not even the right, no, that is the right water. Compare water, silver, and what's that? I guess there are only 2. That's going to be silver. So our reducing agent, and then we'll just combine them. So nitrate and H+, we saw that earlier. It's just going to be nitrate plus 4H+, plus 3 electrons, yields NO gas, plus 2H2O liquids. And then the silver we have to flip over, because silver over here in this reaction is a product. We don't want it as a product, it's got to be a reactant. So we're going to flip this equation. Flip the equation to make silver a reactant. So we're going to go silver solid goes to silver ion plus an electron. And then we have to add them up. So what do we have to do here? Yeah, very similar. Here we need 3 electrons, but we're only producing 1. So what we're going to do is just triple everything on the bottom. We triple everything. Then 3 electrons, match. In other words, we call balancing out the electrons. And then we'll just add up everything. What we end up when we do this method is we end up with the net ionic equation. And so we aren't going to get the CE, the IE, and the NIE. We're just going to get the NIE after we simplify here. So silver solids is going to go to NO gas plus 2H2O liquid plus 3 Ag plus. So this is our NIE. But you got to see, is there driving force? If there's no driving force, then that's not going to happen. So nitrate and H plus, this is our oxidizer. These are our conjugate reducers. Silver ion, that's our reducer. So the opposite side, we have our conjugate oxidizer. So we'll label everything. The oxidizer here, reducer here, NO and water, that's our reducer. Silver ions, that's our oxidizer. And then we'll compare the two oxidizers. Which one's stronger? Nitrate in H plus or silver ion? Nitrate. And so this is a case where we're going from stronger to weaker. If the oxidizers do this, then of course the reducers have to follow because they're the conjugates. I mean the reducer. This is going to be flipped. So flip the. And therefore, silver is stronger. NO is going to be weaker. We can confirm that off the chart here. And so we do have driving force. So single replacement predicted no reaction. That turned out to be wrong. No redox reaction. There is a redox reaction. This is it. Again, we're going to generate a toxic gas, NO, and it's going to react with the silver. In fact, it's going to eat up the silver metal here. Oh, that's a nice piece of silver. Looks like they're doing this on their porch. Let's speed it up. Speed up this way. NO gas is actually colorless, nitric oxide. But NO gas is easily oxidized by air to form NO2. This is that orange-brown gas. There's nitrogen dioxide. That's usually what you see in the smog. See that air pollution. Oh, looks like the silver is gone. Silver nitrate should be soluble. Well, nitrate salts is soluble. Nice crystals. Okay, nice crystals of silver nitrate. Those are nice crystals. Wow. Nice crystals. Right. That's because there's excess nitrate present. Because for every nitrate, we had 4 H pluses react. So we have 3 nitrates left over that aren't reacting. But that we could find out by going backwards from the NIE, doing that. All right, so the chart method is more reliable, but it's still not perfect, One of the problems with the chart is this. Is this chart comprehensive? It's nowhere close to being comprehensive. So what happens if something's not on the chart? If something's not on the chart, Like, there's something, we might use a more comprehensive chart. That chart there has a lot more entries. The chart in the middle of the room. So that's a more comprehensive chart. Or if you go to the Chem 1 book, they have about 6 pages of chart in there. That's more comprehensive too. But some of the other things would be like this, you know, if dichromate's here, then that means chromate, you know, chromate's going to be similar, or if iodate's here, then chlorate's going to be somewhere around here, you know, that kind of thing. And so sometimes you can kind of get an idea of how things react by looking for something that's similar to it here in terms of formula, composition, you know, probably structure. But there are some things that, you know, you should just know that aren't necessarily on the chart. One of the things would be like, you know, methane. Methane is in the news over spring break. Did you hear about it? Methane? It was, it's in the news every single year. It's in the news. But there's a natural gas explosion, not just one. I guess there's more than one. So I just searched it this morning. Harrisburg house explodes after gas leak. Natural gas caused Harrisburg explosion that blew 2 women off the couch, prompted grandma to jump off from the roof. Fortunately, nobody was killed in that one, but that wasn't the one I was looking for. The one I was looking for was this one in Durham, North Carolina. This happened 4 days ago. Deadly gas explosion levels building in Durham, North Carolina.
Part of downtown Durham was leveled by a natural gas explosion. At least 1 person was killed, more than a dozen others are today. The front of 1 building was blasted apart, several others were dead. Windows were shattered with blocks. Some destruction feels like it could. Harold Barnett is a oh my God. Thick black smoke and a roaring fire visible from a mine.
Every year, I don't know how many, every year there are fatal gas explosions. So, methane, you know, sometimes you don't think much about it, but methane is a powerful what? Methane is a powerful acid, base, ion? Is it an ion, methane? No. Is it an acid? No. Is it a base? No. It's a powerful what? Oxygen is a powerful gas too. Is it? I mean, oxygen's a gas. Methane's a gas. Are they both equally powerful? In their own way, yeah, they are. I mean, you need methane, you need oxygen. Methane acts as the what? And oxygen acts as the what? Yeah, it's potential. This is a very high potential energy mixture. Methane and oxygen is a high potential energy mixture because methane is the, and oxygen is the, yeah, oxygen is the oxidizer and methane is the reducer. And methane is a powerful reducer. Now, methane's not on our chart here. I don't see methane on the chart. What's the most powerful reducer on the chart? Lithium. And so we all worry about lithium battery fires. You know, lithium and potential explosions too. There's a plant, a lithium battery plant in Asia that was completely destroyed there. So what is more flammable, would you say? Methane? We Do you remember the magnesium I ignited? Burnt with a bright white flame? What do you think is more flammable, methane or magnesium? I don't know. Maybe magnesium. But nonetheless, aluminum we don't think of being so flammable, iron, zinc, but all these metals are marked flammable because, under the right conditions, they will burn. Like finely powdered iron burns. They use it in sparklers. They give the little white sparks. And so methane would be somewhere around here in terms of being a reducer. And how would you know? You'd have to know that because we need to know some properties. In fact, a lot of organics are flammable. And for something to be flammable, they got to be actually, did I go over time? Yeah, I'm way over time. Let's stop. We'll take a break here.